Example 10.9 is to determine the cam profile for an oscillating roller follower. We assume that the follower deviates while the cam rotates counterclockwise from 0 degrees to 19 degrees. The rise occurs with 3, 4, 5 polynomial motion during the cam rotation from 19 degrees to 118 degrees, and the cam rotate angles required beta is 19 degrees. The follower then deviates for 19 degrees of cam rotation, and the return occurs with the harmonic motion for the cam rotation from 217 degrees to 316 degrees, and the cam rotation angle required beta is 19 degrees. Amplitude of the follower oscillation is 13 degrees. Several main parameters are given. Radius of the base circle RB is 2 inch. Radius of the roller R0 is 1 inch. Distance between two pivots R1 is 6 inch. And the length of the follower R3 and the initial angle phi 0 can be calculated according to the given initial position of the mechanism. In this case, the cam rotates counterclockwise, so the variable SGN is equal to -1. We have 4 intervals here: low devier, rise interval, high devier, and the return interval. We compute the cam profile points using 10 degree increments from 0 degree to 316 degrees. Later, we need to use the cam angle to calculate the x and the y coordinates of the cam profiles. So I convert its unit from degree to radius. The rise and the return will not always start at theta equal to 0. To simplify the equations, we can use a simple coordinate transformation and shift the origin of the coordinate system to start the equation at 0. So we subtract the initial angle from the cam angle. Let us see the rise interval. We have 3, 4, 5 polynomial like this, and its first derivative like this. Here, the first derivative needs to consider the variable SGN. Here we use an absolute reference $J, $6 to reference it. Then substitute the values into formulas for cam coordinates listed in table 10.11 of the textbook. We can get values of B, lambda, R, gamma, and the x and y coordinates of the cam profile. Let me see their formulas. For B, here. For lambda, here, we use arctangent tool. For R, here. For gamma, here. We also use a arctangent tool. And for X, here. You can see the theta need to consider the variable SGN here. And the Y here. There are two functions for calculating the inverse tangent function, arctangent, in Excel. These two functions are arctangent and arctangent 2. Because we want to return angles in all four quadrants of the unit circle, we use arctangent 2 function here. The Excel arctangent 2 function returns arctangent in radius of the xy coordinates. We need to consider the variable SGN for determining x and y coordinates. In this case, the candle takes counterclockwise. SGN is equal to -1. The can angle will be negative. According to the formulas for the pressure angle listed in the table 10.11 of the textbook, we can get zeta, BE, sine, and epsilon. Here, epsilon is the pressure angle. We can use the Excel degrees function to convert the unit from radius to degrees. We note that the pressure angle is not zero during the loaded wear. This result violates our initial assumption, so something wrong is happening. Let us see the definition of the pressure angle. The pressure angle is the angle between the velocity of point B3 and the normal line to the surface at the contact point. The direction for the velocity of point B3 is perpendicular to the link BE. The normal line to the surface at the contact point is line BD from the contact point B to the incident center DI23. For the dewey position, point A and D coincide with each other. In this case, the follower gives zero pressure angle in the initial position. The textbook says the angle ACE is 19 degrees, but from this figure, we know it is not correct. Actually, the angle ABE must be 19 degrees for pressure angle to be zero during the initial dewey. Therefore, from the right triangles ABE and CBE, we can compute R3 by this formula. I multiply the value of R3 into 5.744 inch. You see, we can get the pressure angle is zero at low dewey positions. We can use Excel scatter with smooth lines and the marks function to plot the diagrams for the cam profile and the pressure angle. Let's take a look at the cam profile diagram. I select the diagram and press the right mouse button. Select data and edit. Series S value are X coordinate, and the series of Y values are Y coordinate. And take a look at the pressure angle here. Click select data, edit it. So you can see series S values is cam location angle, and the series Y value is the pressure angle epsilon. I will show you how to use finite difference to compute the radius of curvature for a cam profile. If we have a parametric expression for a cam geometry in terms of x of theta and y of theta, we have formula for a radius of curvature rho like this. If the expressions are complicated and difficult to find their first and second derivatives, we can use numerical differentiation to find the numerical values of derivatives. In this case, we use the second-order centered difference approaches mentioned for the first and the second derivatives. We give a finite delta theta is equal to 0.01 degrees. We calculate 3 sets of the coordinates of the cam profile based on 3 cam angles, theta minus delta theta, theta, and theta plus delta theta for each cam rotation angle theta. For example, the cam angle is 19 degrees. We compute the coordinates of the cam profile for cam angle 19 degrees, 89.99 degrees, and 19.01 degrees. We can get SY x minus 1, y minus 1, and x plus 1, y plus 1. Then we can get the first and the second derivatives of x and y coordinates based on the final difference formulas. Here, for x, y, second derivative for x, y, then We apply them to compute the radius of curvature. For the radius of curvature, we need to consider the variable SGI too. Again, we use Excel scatter function to plot the radius of curvature diagram here. Anyway, from the videos today, you already learned about using the analytical method to determine the cam profile, pressure angle, and the radius of curvature. I hope you can watch the videos and read the textbook before the class. Well, see you soon.